Okay, we're going to continue in Chapter 7, which has a lot of material in it, to talk about um, another aspect of sort of a complementary part of an existence proof, which is the idea of a uniqueness proof. So sometimes when we claim something exists, we just mean that there is something, but there might be lots of them. An example is Pythagorean triples. We gave an example of one Pythagorean triple, 3, 4, 5. But there are lots of other ones that you can find. And we're satisfied if we can just show you that there's one. But sometimes we want to show more. We want to show that not only does something exist, but only one of that thing exists. And that's where a uniqueness proof comes in. So because uniqueness, we say that something is unique, meaning it's the only one of its kind. So when we claim something is unique, we mean there's only one thing of that type. And here's a very straightforward example. The proposition is there is a unique real number a such that a is bigger than 0 and a squared equals 1. And the thing to understand about this proposition is it's making two claims. First, that there exists a real number a so that a squared equals 1 and a is bigger than 0. So that's an existence claim. It's just saying there is an a whose square is 1 and which is positive. But the other thing that we're saying is that there's only one real number with these properties. And that's a stronger assertion. And the way uniqueness proofs usually go is like something like this. So the theorem says something like there exists a unique x such that p of x is true. And the way you prove it is you first show there is an x so that p of x is true. And then you imagine that you had two things for which this property holds and show that in fact those two things are the same. So maybe it's a bit long-winded, but remember that the earlier example was there exists, so this was a proposition, there exists a unique a such that a is bigger than 0 and a squared equals 1. So the proof of existence, so first observe that a equals 1 is greater than 0, and a squared equals 1 is 1 squared, satisfies a squared equals 1. So therefore we've shown, so at least one a with the desired property exists. Namely 1. But now we have to show it's the only one. So suppose we show uniqueness. Now we're going to show uniqueness. So suppose a squared equals 1. Then a squared minus 1 equals 0, or a plus 1, a minus 1 equals 0. Therefore, a equals plus 1 or a equals minus 1. If a is bigger than 0, then a equals plus 1 is the only solution. So we've shown that not only is plus 1 a solution, but it's the only one. Now, we're going to take on a more daunting task here by going back to Euclid's algorithm and returning to a question which came up in our discussion of Euclid's algorithm. So let me first state the proposition and then remind you where it came up. So suppose we have two natural numbers a and b. Then there is a unique natural number d with the following property. M is a multiple of d if and only if m is ax plus by for some x, y, and z. What is this proposition telling us? This proposition is telling us that if you look at the collection of numbers ax plus by, there is some d that tells you that all of those numbers are the multiples of d, and vice versa. And you remember, we sort of noticed that when we did our grid calculation, we saw that if the GCD was 1, it looked like we could get every number in our AX plus BY grid. And if the GCD was 3, then it looked like we could get all multiples of 3 in our AX plus BY grid. And that's what this proposition is saying. It's saying that if you look at all the combinations AX plus BY, then it's exactly the multiples of a number D, and that number D is determined. It's uniquely determined, and we know what it is. It's the greatest common divisor of A and B. So from a logical point of view, there's two things we have to deal with. We have to show, first of all, that there is a D that makes the if and only if statement M is a multiple of D if and only if M equals AX plus BY for some X, Y, and Z true. And then we have to show that there's at most one that has this property. We kind of already know that there is one, namely the GCD, but we'll work through it carefully to see exactly what it is that's going on. In some ways, I think the hardest part about this proposition is just understanding the logical structure. That you have this existential quantifier, there exists a unique D in D, such that, and then you have an if and only if statement. And so the claim is that if you look at the collection of D, which makes this if and only if statement true, there's exactly one D. So let's try to prove this. And it's, as I said, a lot of the ideas are already in our discussion of Euclid's algorithm. So we have to do two directions. We have to show first, as I mentioned, that there is a D. And then for that D, we have an if and only if statement. So we're going to have to do two things. First of all, show there is a D, so that first M is a multiple of D implies M equals AX plus BY, and then the opposite. And then we have to show that there's only one such. So I should say you have to do both of these things, because sometimes in a uniqueness proof you can prove that there's at most one thing that has this property, but in fact there might be 0. So we have to make sure there's at least one. Okay, so here's step 1A. We have to show that there exists a D, and I'm going to give it to you. I'm going to tell you D is GCD of AB. And now I have to prove that it has the right properties. And in particular, we have to show that if you're a multiple of the GCD of A and B, then you're a linear combination AX plus BY. And if you're a linear combination AX plus BY, then you're a multiple of the GCD. So as I point out here, we are going to show that D makes the if and only if statement true. So first we show one direction of the if and only if statement, namely D divides M implies M equals AX plus BY for some X and Y. So we assume that D divides M, so M is a multiple of D, meaning M is D times G for some integer G. We use what we proved in Euclid's algorithm to write the GCD as a linear combination AK plus BL, and then we multiply both sides of this equation by G, and we get GD equals AGK plus BGL. And DG is M, so we've written M as a combination of A and B, replacing K by GK and L by GL. If you think back to the discussion of the grid, we did this in the case where once we had found 1 was 7 plus 3 times minus 2, then we showed that, for instance, 5 is 7 times 5 plus 3 times minus 10. Namely, once you get D, you can get any multiple of D by multiplying the coordinates. So this direction we've already done, and we've shown that every multiple of M is of the form AX plus BY. But we're not done yet. We have to go in the other direction. Now we have to show that if M is a multiple, AX plus BY, a linear combination, then it's a multiple of D. And for that, we use the fact that we already proved that we know that D is the greatest common divisor of A and B, remember. So A is a multiple of D and B is a multiple of D. And if we substitute that into this equation, A is UD and B is VD, we get M is UDX plus VDY, factor out the D, and we see that M is a multiple of D. We also did this in our discussion of the grid, where we observed that any linear, if A and B are, say, both multiples of 3, then whatever combination you take is still going to be a multiple of 3. So since A and B are multiples of their greatest common divisor, any combination is still going to be a multiple of their greatest common divisor. And that's what we're using here. So in some sense, all of this was implicit in the proof of Euclid's algorithm. But we have to show that D is the only integer that makes this if and only if statement true. And as I mentioned, a lot of times in these uniqueness proofs, what we do is we assume that we have another one and show that it's equal to the one that we started with. Okay, so suppose we've got our D prime and it makes this if and only if statement true. And so what that means is that this G here, this integer which makes this statement true, is D prime. And now we are going to show that D prime is less than or equal to D. And the first thing to notice is that we can take M to be A because A is A times 1 plus B times 0. And in that case, the if and only if statement, since A is equal to A times 1 plus B times 0, the if and only if statement tells us that D prime divides D. And, sorry, divides A, because M is A. And the same thing for B. B is A times 0 plus B times 1, and therefore D prime divides B. And if D prime divides both A and B, it's a common divisor of A and B. D itself is the greatest common divisor of A and B. So any common divisor has to be less than or equal to the greatest common divisor, and so D prime is less than or equal to D. To go the other direction, we have to show that D is less than or equal to D prime. And if we go back to our if and only if statement, now we let M be D prime. So we have D prime divides D prime, and that implies that D prime equals AX plus BY for some X and Y. So we use the if and only if in the other direction. Now, we know that A and B are multiples of the greatest common divisor, so we write them as multiples of D, which is the greatest common divisor, and substitute that into this expression, and we get D prime is D times UX plus BY. And that tells us that D divides D prime, so D prime is bigger than or equal to D. So up above, we had that D prime was less than or equal to D. Now we have that D prime is bigger than or equal to D. So the conclusion is that D prime equals D.